All right, so we've introduced the idea of configuration space and how I can describe a system's configuration, and we talked about how we could narrow down the number of coordinates that we need to define in order to do that. And now to work ourselves towards dynamics, we had this idea that if you are moving from one configuration to the next, there's infinite number of ways you can potentially do that. But nature seems to pick one particular path and going from one configuration to the next. And we're still trying to work towards how do we figure out what that optimal path is? That ultimately becomes summarized in something called the principle of least action, which the paraphrase of this might be to say that nature is lazy and chooses some sort of optimum path that makes it easiest as possible on nature's behalf. It might sound silly. We'll see there's actually some honest truth to this. Lazy might not be the right word, because it actually turns out that while it's called the principle of least action, it's actually that nature is doing some sort of optimization when it decides what path actually is going to be taken out of the infinite number of paths. You can go from one configuration to the next. So sometimes you'll see this written as the principle of stationary action, but that sounds, less meaningful. But what it's ultimately trying to say is that there is an optimization process that is being done, and nature is choosing that optimal path, which can be, for example, we've thinking of how you do optimizations, where you find extremum of particular functions, right, where you might be finding maxes or mins, right? So it might be that nature is taking the easiest path or the optimal path. So maybe it's more fair, actually, now that I think about it, not to call nature lazy, but maybe nature's being efficient in deciding what path it's going to take from one configuration to the next. And it turns out this little sentence will allow us to derive the correct equations of motion for many systems. Actually, really for all systems in and out of classical mechanics. But I thought I would start first with kind of two motivations of examples where nature seems to be doing optimization. So two motivations of nature doing optimization. One relies to the idea of potential energy. Potential energy, remember, is that we can have some sort of scalar function u, that is the potential energy function, and that encapsulates knowledge of forces, such that if I take the negative gradient of this potential energy function, I get back forces. We talked a little bit about that already. And we had some drawings that when we're dealing with a force that's in a one-dimensional force, so it might only be a function of x, I can define a potential energy function, and it might look something like this. And the force that ends up being kind of negative the slope of this line, right, because the gradient just becomes df or du dx. And we talked about how in cases like this, in 1D, then negative du dx equals f. So places of equilibrium, so f equals 0, which again is equilibrium points, occurs when du by dx is equal to 0. Points of equilibrium occur at extremum. So this dot down here is an example of an equilibrium point. This part up here is an example of an equilibrium point. Particularly, we also talked about how this bottom one is an example of a stable equilibrium point, where this is an example of an unstable equilibrium point. If you can stay at the top of that hill, you'll stay there forever. But any slight nudge is going to take you away from the top of the hill. The stable equilibrium points means that if you had something like friction that was slowly but surely damping away your total energy, you're going to tend to want to fall. If you were an object, if I would say an object that was located here, right, I might oscillate back and forth. But if I was undergoing some dampening, I would slowly but surely settle and reach this point of stable equilibrium. And since friction is usually present in most cases, nature tends to move towards locations that are minimum, or locations that are minimums of the potential energy function. As your energy ebbs away, you're going to find yourself in some sort of minimum potential energy state. And again, that's not always the case because you have these unstable equilibrium as well, but those are hard to maintain. Again, any slight nudge away from the unstable equilibrium point and you roll away. But there's an example of like things on it, over time tend towards these extremum, in this case, an extremum or a minimum of the potential energy function. There's also some examples of this regarding light and how light travels. One of the earliest examples of this was actually Hero of Alexandria. This, I think, is around like 2000 BCE, where they identified in reflection, light minimizes the distance it travels between 2 points. So if you have some starting point here and some ending point here where the light eventually ends up, and you do know that a reflection occurs, that the path that light beam takes is one that minimizes the distance between the 2 points while also including some sort of reflection. And this you can then work out ends up resulting in the incident angle matching the reflected angle. That kind of naturally pops out as a result of this idea of light doing an optimization when it goes from one point to another when reflection is involved. So there, light seems to be doing some sort of minimization of distance. Turns out this doesn't work in general if you then include refraction, where light bends when it goes from one medium to the other. This is not the optimization that light is taking, but Fermat actually explored this a little bit more and actually could take it even further in a way that explained both the path that light takes when it's reflected and the path that light takes when it's refracted through a medium. So this is ultimately gets down to Fermat's principle, where light minimizes the proper time it takes between 2 points. Proper time, of course, being what you defined when you took modern physics or some sort of intro to special relativity. So let me give you an example of what this is and how this kind of looks. Let's do an example of you. Suppose you are a lifeguard on the beach and you are located here at spot A. And you notice down the beach, still on the sand, there is someone located at spot B that needs your help. And you, the lifeguard, want to get to spot B as fast as possible. What path would you take? You would be doing an optimization problem in your head, and since the entire beach is the same as just sand, you would decide that the way to get there the fastest is to travel in a straight line between the 2 points. If you knew that your velocity was a certain velocity, or if you knew your speed was a certain speed when you're on sand, in order to then minimize the time, you should minimize the distance, since your speed is going to be the same everywhere on the beach. Make sense? But now what about the case where, again, you're still starting at A and you're trying to get to B, but B is located out on the water. So they're sitting out on the water, and you now need to decide how to get to this person as fast as possible, knowing also that you can run faster on sand than you can swim. Well, in this case, you wouldn't take a straight line, because that would involve you being in the water more than you need to be, knowing that you can run faster on the sand compared to swimming in the water. So what you might do instead is spend more of your time on the sand and then have some amount of distance that you take in the water. And that is the path that you would ultimately take to get to B in the shortest amount of time. So again, you've done an optimization here where you're trying to minimize the time it takes, taking into account that your velocity of sand is different than the velocity you have in the water. Light, it turns out, does the exact same thing, right? This picture might look familiar, right? If you remember kind of refraction from intro physics, and usually it was kind of diagrams that looked like this, where light, when it travels from some point here at the top and ends up at some point here in the bottom, you could consider those 2 points fixed. What is the path that will result in a beam of light starting at A and ending at B? It does take a path that, it turns out, you can calculate, minimizes the proper time that it travels. Because in this case, it is traveling at different speeds through the 2 different mediums, because water has a higher index of refraction than air, say. So light does seem to be doing an optimization problem, and it turns out that if you use this fact of minimum proper time, you can actually derive Snell's law, which we call Snell's law was at the index of refraction times the sine of the incident angle, where the index of refraction is for the kind of material the light starts in. It then bends when it goes into a new medium with a different index of refraction, and the refracted angle is given by theta 2. This can be derived on this assumption that light is doing an optimization. So it does seem like these are examples, at least, I've given you kind of 2 examples, to motivate the idea that there is some optimization that's going on in nature. Though these are obviously more challenging than just finding the max and min of a function. The max and min of a function, we talked about, if you have some sort of function, I can take its derivative, I can set that equal to 0, or I could set its gradient equal to 0 if it's multidimensional, and I can find these individual points where it is a max or a min. To find a function that minimizes, say, the proper time, or the distance between 2 points, is a little bit more complicated because we're considering all possible ways you can go from point A to point B, the infinite number of functions that you can write down. And one of those presumably minimizes some sort of quantity that we can then calculate with that function. So it's similar in this idea in that we're looking for an extremum, but it's not as simple as just taking a derivative and setting it equal to 0. Let me show you kind of what we mean by this. Suppose you have a unit grid where in the lower left-hand corner that's 0, 0, and the upper right corner that's 1, 1. And I want to ask, what is the shortest path from 0, 0 to 1, 1? What, if we use axes x and y, what function y of x, which defines your path, gives you the minimum distance? Now, of course, you're saying it's, of course, a straight line. But how would we calculate that? What am I actually calculating? If I give you a function y of x, what then do you have to calculate in order to get the total distance of that path? Well, so the idea is that we're given f of x, or y of x, and we also know that y of 0 is 0 and y of 1 is 1. We start in the lower left, we end in the upper right, and we want to measure the path, or the length of the line that's drawn, right? So if it's just a straight line, how long is that line? But I could take, say, a parabolic path that looks like this, right? And that has a different distance. If I just use a ruler to measure how long that red line is, I could do something like this, and maybe I loop around a little bit and go up. That has a different path. I could write a function down that makes me take that path. Or I might go along the edge. That might be another path I could take. These are just 4 examples of an infinite number of examples that I could then calculate the distance of that path and see which one of them is the shortest. So in this case, we can define what will be called a functional S. So we can define S, which is going to be, in this case, the path length. In this case, this is what I want to optimize, right? I want to find the path. I want to find the function that optimizes this S, which is going to be the path length, which the path length is then just integral of ds. I break my little path into a bunch of tiny little segments and start counting all those little segments. That's just the same thing as dx squared plus dy squared all in the square root. And then if I want to turn this into something where I can plug in a function for y, I might yank out a dx out of the square root. So if I rip a dx out of the square root, the dx squared comes out, and then this becomes dy by dx all squared. That's all under the square root over dx. And this is an integral, of course. So I've turned this into an integral over x, where if I provided a y as a function of x, I could take the derivative, I can plug that in, and then I have the square root thing, which I can then integrate between x equals 0 and x equals 1. And that would give you the path length. You might have done this in like Calc 2 or 3, right? A path length formula. So this S here is what's called a functional. Not a function, but a functional. Because as input, it takes functions. Right, a function, you plug in a number and it spits back out a number. Here you plug in a function and then it spits back out a number. So we call that a functional. So S in this case, we might imagine S can be a function of, say, y, might involve y dot, might involve t all by, or in this case, x all by itself, right, the independent variable. Right, so in this case, it looks like it's just a function of, I guess I shouldn't use y dot because this isn't time, right? So it might be a function of y, or dy dx, or just the independent variable x itself. In this case, it looks like the path length is just a function of the derivative. So for example, if I said that y of x is just x, the straight line that goes from the lower left to the upper right, it satisfies my boundary conditions. Then I know dy by dx is just 1. Then I know this integral x, or this integral for s, that looks like it's the square root of 1 plus, and this just becomes 1 squared over x. Or it looks like it's the integral from 0 to 1 of the square root of 2 dx. Or this is just equal to the square root of 2. Again, not too surprising because I know, or I could have just thought of this geometrically. That's just the hypotenuse of a triangle where both sides are unit length. But that would be the evaluation of this functional s for a particular function y of x equals x. I could then do y of x equals x squared. That's also a path that goes from the lower left to the upper right. Then dy by dx equals 2x. Then s in this case is an integral of 1 plus 2x squared on the square root dx. And that ends up being not the greatest integral to evolve analytically, but you can do it. It ends up being 1/4 and brackets 2 times the square root of 5 plus arc sine of 2. And then that approximately is about 1.479. As compared to the square root of 2, which is about 1.414. So the path length of this parabola going from 0 to 1 has a length of about 1.479, which notice is greater than the path length for the straight line, which is only 1.414. You might try the case where you kind of go along the edges. So you have kind of y of x equals 0 for the first half. That's when you're kind of just going along the bottom. And then you have kind of x of y equals 1 when you're kind of going up along the edge. And then you could ask, what is the total path length for that path where you go just horizontally and then you go purely vertical? Well, obviously in that case, it better just equal 2, all right? Because you go 1 to the right and then you go 1 straight up. And so notice there the path length is 2, which is also greater than the straight line that was just y of x equals x. And that also happens to be greater than the parabola that went from 0 to 1, 1. So of these three examples, it does seem like the straight line that diagonally goes from one corner to the next is the extremum of these three particular examples, because it's the one that has a minimum value for this path length. Unfortunately, that does not yet prove that the straight line is the one that optimizes this particular integral, because this is just one example. These are just three examples of infinite functions that can start in the lower left and end up in the upper right. When you have an infinite possibilities, how are you actually going to try them all? We just did three examples here to try to motivate the idea. Let me write down kind of what this is. So this S here, which in this case ended up being the path length integral, is an example of an action integral. Actually, I think I will use a different color of an action integral. There's some quantity in this case, the path length that we want to evaluate, that we want to optimize. S is then the value of that quantity. For a given function. Because again, the idea is this is a functional. I can plug in different functions in order to try to evaluate this particular action, which in this case is the path length. For other problems, it might be that you want to minimize the time that's taken. I could go back to the example of the person trying to save the drowning person. Maybe they start here at 0, 1, and the person that's drowning is over here at 1, 0. And we know, for example, right, so that if there's water here, if we want to minimize the time taken, right, the action in this case might be an integral of time. Right, and it's going to be, I need to write down some integral that will evaluate the time it takes to go from the upper left to the lower right. That might depend on, and the function might be then the exact path I take. So I could possibly turn this into, for example, a path length integral, knowing that the velocity that I can move is going to depend on my position. Right, where am I, and how fast I can move might depend on whether I'm in sand or water. Or this might be a more complicated function. This velocity might be a more complicated function of x and y. Like maybe it's some, if you're trying to navigate yourself, around a hill or a mountain or something, how fast you can move might depend on the elevation or the slope of the elevation, for example. So then this action integral might be something like 1 plus dy dx squared all the square root dx. But then this is all being divided by some velocity function that might depend also on x and y. So then I have to write down a path. So then you have to tell me, right, a path y of x, which might be a piecewise function. It might not be. I can then evaluate dy dx, and I can then plug it into this integral and then try to evaluate that for a particular y that's a function of x. That then will tell me the total amount of time it takes me to travel for that particular path, and then I have to consider alternative paths and see which one of them is going to actually minimize the amount of time it takes. Again, that might seem quite daunting, right? To then have to try to do an infinite number of possibilities. So let me do kind of one more motivation of this before the next module, which will launch into a proof of how we can actually find that particular optimal path. One way you can try to, you might think, how am I going to try an infinite number of paths? It might be possible that you could parameterize your paths such that you can do one integral that actually constitutes an infinite number of paths. So if we go back to the case where we want to find the shortest distance between the lower left corner and the lower right corner, right, you might say, well, I'm going to parameterize y of x to be, I'm going to do x plus maybe alpha sine of pi times x. And again, remember, x goes between 0 and 1. Think, what do these paths look like where alpha is a constant? That could be positive 0 or negative. Well, notice in the case where alpha is 0, that's just the path. That's a diagonal line. That's alpha of 0. When alpha is positive, and again, notice the sign, right? When x is 0, the sine of pi x is 0. So that entire right-hand side disappears. You get y of x equals 0. That works when x is 0. When x is equal to 1, sine of pi is also 0. So then you still get the right limits, right? You start at 0 and you end at 1. So notice if alpha is positive, that might look something like this, where you kind of curve up, but then eventually end at your endpoint. Or if alpha is negative, that might be when you kind of loop down below and then eventually end up at your endpoint. So if I let alpha be a constant and don't specify its number right away, maybe I could evaluate this integral and determine, for a whole class of functions, which alpha particularly minimizes the path I'm taking. Maybe that can help me start to narrow down all the possible paths. So in this case, you have s, which again was the integral of 1 plus dy dx squared. The path length integral is 0 from 0 to 1. We have a function for y. I could take its derivative, plug that in. So it looks like this is the integral of 0 to 1 of 1 plus, that's 1 plus pi alpha cosine of pi x. And that's all squared in the square root dx. Now I could try to evaluate this for some constant alpha. This actually ends up being quite hard, but you could do this numerically. So I'll make a little table, right? For various values of alpha, what is the value of s that you get? Well, of course, when alpha is 0, you get the square root of 2. So you get something like square root 1.14142. When alpha is plus or minus 10 to the minus 2, you get something like 1.4143. When it's plus or minus 10 to the minus 1, you get something like 1.4231. And the bigger that alpha gets, the bigger the action integral gets. So again, if you look at these three numbers, it does seem that when alpha equals 0, the value of the action integral s is minimized. And remember, when alpha equals 0, that just corresponds to y of x equals x, which we happen to also know is the right answer. But again, these are just a few examples. This has not yet proven that y of x equals x is the shortest path. Because again, while this is a whole class of functions, and the bigger alpha gets, the bigger the answer gets. So you might say that we've done this for an infinite number of values of alpha. Though again, really, I've just shown 5 examples here. This still doesn't capture every possible path that gets you from the lower left-hand corner to the upper right-hand corner. Because, for example, this function here does not capture, for example, the path that has you go just up along the left and then right across the top. Right? No value of alpha is going to give you that path I just drew in blue. Nor is it going to give you a path where you kind of do a loop and kind of spiral your way up. We have not yet tested whether that path has a shorter distance. So again, this kind of brute force trial by error, try to dream up the function and plug it in and see which one minimizes this functional, is not going to work. Or at least it doesn't work in practice if we really do want to find the optimal path. But this also doesn't mean that all hope is lost. Think back to Calc 1 when you were trying to find the max and mins of a continuous function. For a continuous function, that means there was an infinite number, even if you were to say, like, find the max and min between x equals 1 and x equals 3 for a given function. Even in that range, there's an infinite number of x values that you could plug in. And obviously in Calc 1, you did not sit and start plugging in every possible x value into the function, trying to find which one minimized or maximized the function. You had a procedure, namely take the derivative and set it equal to 0, that allowed you from the infinite possibilities to pluck out exactly the right specific values that worked there. So we need to come up with a way that's similar to that, where I can have some procedure that when solved, it will tell me exactly which particular function is going to be the solution that will optimize this particular integral. Or if I wanted to write down other examples, right, there might be an action integral. This actually does show up. We'll see a physical example of this. Or it might be an integral where I just want to find what is the function y that maximizes this integral, right? I take the derivative, I square it. And just to give you a little hint as to kind of where this might show up for us, let me actually change and make my independent variable t instead. Right, it might be, maybe I want to ask, is there a path that might maximize or minimize this particular integral for some constant m. Right, there might be some path that's optimizing this particular integral, which seems like it might have something to do with kinetic energy, for example. All right, so again, of all the infinite possibilities I could plug in for y that is a function of t, which ones will make this integral a max or a min, given two starting configuration and an ending configuration, which if we think for just a single particle for right now, right, some starting point and some end point, what path between those 2 points will optimize this particular integral, for example. To tease kind of what this is ultimately going to be, we're going to come up with a procedure in the next module that will ultimately give us not a function, but it will give us a way to come up with a differential equation that when solved, that solution to the differential equation is the one that optimizes a particular action integral. And then in the module after that, we will make the huge leap forward in our understanding, and that we will see that nature is choosing to optimize a particular action integral. We've been kind of just working very generally, where action integrals have been, times or distances, or this one I just wrote down that looks something like a kinetic energy. But there's a particular action integral that nature optimizes. And it turns out that ends up being equivalent to Newton's laws of motion and actually more valid beyond just the classical realm. So we will develop that proof in the next module.